welcome to project 3.8, the 4517 gray code decoder, my final project as an ACE. So quick demonstration. Up here, I have an absolute rotary encoder, and what's special about it is that it's a gray code encoder. So it's not outputting traditional binary on its outputs here, it's outputting gray code, which I'll get into more later, but essentially what's special about gray code is that between adjacent numbers, only one bit changes at a time. So we can see if I scroll through, it goes 0, and then after 9, it continues in hex. It was already in hex, but it becomes obvious that it's hex, so we go A, B, C, D, E, F, and then it overflows again back to 0. And we can also go backwards. And then one other feature about this is if we set this to 0, and then we flip all these switches, it'll now use this gray code counter, which I've built from a standard binary counter, and it'll count up to F and then reset. And then one final quirk of this is if I turn off the the highest bit, one interesting feature of gray code is that it will now count up to 7, then down from 7, and that's just due to the way that the gray code digits are structured. So that's a quick demonstration. One thing to note, this all here is combinational logic, which is used to decode the 4 inputs from here to 7 outputs on here. And the way that this circuit was created was using a technique called Carnot mapping. So let's get into how that works. Okay, so let's say we have the following truth table. And the first thing to note is that the truth table is actually in gray code. And gray code, as I mentioned earlier, is basically a version of binary where only one bit changes between adjacent numbers. So here we have 0, 0, 1, 0, 1, 1, and then we have 1, 0. This was 0, 1. So we have 0, 0, 0, 1, 1, 1, 1, 0, and in normal binary, these two would have been swapped. So that's the only change to consider for now. And then the same thing happens on this axis. So in order to do Carnot mapping or K-mapping, this is what you do. So let's say we have this truth table, which is in gray code, as I mentioned, and we want to call the output, let's call it X. Basically what you do first is you look for groups of powers of 2s of 1. So you're going to look for 1, 1, 2 1s, 4 1s, or 8 1s. The bigger the group of 1s, the less literals or letters you need to represent it, so the less gates. So the simpler the combinational logic circuit. So first we're going to look for groups of 8 because that would use the least number of literals, and we can see there's no groups of 8. One thing to note is that terms can wrap around, so these two are technically considered adjacent terms. But with that, let's get started. So first we can see there's a group of 4 1s here, so we're going to circle that. And then you have to ask yourself, what stays the same between all of those 1s? So it's pretty clear here that the only things that stay the same are A0 and B0. So then in the expression for X, we're going to have A0 and B0. So those have all been covered. The process repeats then until all 1s have been accounted for. So then the next one is this group of 4 here. And if we look what stays the same, we can say that the so A is the same in all of them, B is not the same in all of them, and C is the same in all of them. D, not D, so not D. So then we have the original 4 or AC, and then we still have some 1s, so the process continues. So now we're out of groups of 4, so we can do a group of 2. In this group of 2, we can see that the C0 and the D0 stay the same. But then if we look closely, we can also see that B stays the same. So we have B and C0, D0. Finally, we've got to account for this one, and so we can do a wraparound for this. So that one and this one. So we can see that we have D, C0, but then we also have A0, which remains the same in all of them. Finally, there's this last one, and while we could group it in a group of 2 like this, it's more efficient to group it in a group of 4 because then we only have two literals. So that term would be B0 D. So now we have this expression, which is great, but what do we do with the expression? Well, the expression is basically an algebraic representation of this truth table. Since this is a Boolean algebra statement, not a regular algebraic statement, we can actually implement it really easily with logic gates. So let's see what that looks like. So this circuit represents this expression, which was derived from this truth table. So essentially, this process was repeated for each segment, as we can see here, A all the way through G, and that gave us an equivalent logic gate expression like this, which was simplified as much as possible in order to create the 4517 gray code. The final thing to note is the fashion in which the automatic counting was created. So the way it works is there's a normal 4516 counter, which just counts from 0 to 15 in binary. And essentially, these values outputted by the 4516 were just converted to gray code. So let's call this Q0, Q1, Q2, Q3. To create a gray code counter, bit 0 of the gray code, so let's call it G0, is equal to Q0 XORed with Q1. G1 is equal to Q1 XORed with Q2. Gray code 2 is equal to Q2 XORed with Q3. And gray code 3 is simply equal to Q3. So this can be easily implemented with simple XOR gates. We can call it the 4516G, which paired very nicely with our created 4517G. On that note, thank you so much for watching to the end of this video. I hope you learned something about gray code, Carnot maps, or binary counting in general. Thank you.